right, welcome to your very first engineering mechanics lecture, and we start of course with the warm-up, and the warm-up is fairly familiar to you. Hopefully most techniques that we use mathematically in this section you know about already and you have learned about before, but we will look at them from a more engineering mechanics standpoint, and of course I explained to you throughout this session what that means. Mathematically and conceptually, the warm-up part, the first third of the semester, is significantly simpler than the stuff that we tackle in part number 2. So right now we're in part number 1, and everything in part number 1 will make up one exam, and then we have part number 2, which will make up another exam, and part number 3 will make up another exam. And please do not confuse the simplicity in part number 1, the warm-up, with part number 2. So the reason I'm saying that is I don't want you to think that the effort that we put in part number 1 is equivalent to part number 2. Part number 2, as you will see later throughout the semester, will require much more effort, and this is not because it's necessarily more difficult, it's just more new to you. So in the warm-up, you will deal with things that you have learned before, whereas in part number 2 and part number 3, we will tackle topics that you have never seen before, unless, of course, you have taken engineering classes before or you have taken engineering mechanics before. So this is just a little warm-up, and we just ease into the topic, and the real goal of the warm-up here is to familiarize you with the work style in this class and with all the methods we're going to use, so that you can get used to it. And then when we really learn engineering mechanics, the core of the class, part 2, then you have all the tools in place and you're ready to move forward. So with that said, let's get started and let's have a look at our very first lecture. All right, welcome to your very first lecture in engineering mechanics as part of our first chapter. And in our first part or first chapter, we deal with forces, and we want to really develop a solid understanding of forces. So my goal in this lecture here is to give you a very broad overview first and give you an introduction to talk about Newton's laws, because this is really at the heart of everything we do. Don't get me wrong, what we discussed here today is something that you don't have to have consciously on your mind all the time, but everything we do in this class really results from all the stuff we talk about here. So with that said, let's dive into the objectives of today's lecture and let's think about what we want to cover today. First off, we need to recall some physics principle and talk about some general concepts for mechanics. And we're going to do that on a very broad level that will set the tone for all the methods that we use in this class. Then we want to differentiate the two systems that we as engineers deal with. We deal with the Imperial System. Often engineers in practice deal with the Imperial System, but then often engineers in science deal with the SI system. It sometimes even depends on your discipline. If you're like a chemical engineer or a civil engineer, then you may use or prefer one or the other, but we want to talk about both of them. So the goal here is to talk about the two measurement systems and think about them very broadly, just as an introduction. Then the most important part I would consider are the Newton's laws that we want to talk about. Of course, you have heard about them before, but I want to give some special attention to some of them. And another thing that we learn from Newton's laws is the gravitational attraction. That is the reason why we can even deal with loads in this class or in engineering mechanics. And so we want to understand how that works, and we want to understand how this leads to actually weight on the system. So let's get started and let's begin with a short introduction to mechanics. So how do we deal with mechanics in this class, or how do we want to think about mechanics? So first of all, mechanics is a sub-branch of physics. And in other words, we need to understand what physics is, right? And physics is really the description of nature, right? So physis is Greek for the description of nature. And so really physics tries to explain nature and the universe, if you will. So we use mathematics to explain the universe. So use mathematics to explain nature and the universe. So we know that physics expresses the world around us, and we know that mechanics is a sub-branch. So what sub-branch is mechanics really? So mechanics really deals with specific types of physics. And that is, we deal with physics that is concerned with the behavior of bodies or objects under the influence of forces or displacement. So we're really dealing with forces and displacement. Forces, anything that's pushing or pulling on a physical body, and displacement, anything that makes it move in any direction. And this can technically happen at any scale, right? So this can happen at any scale. So for example, you can have atoms which are as small as 5 times 10 to the minus 11 meter in radius. So this is the radius. Or you can deal with objects as large as, for example, as the Earth. And that has a radius of approximately 6.378 times 10 to the power of 6 meters. And so you see that mechanics really can deal with like any size. And here we have differences of 17 magnitudes. But in this class, of course, we deal mostly with structures. And one of the most famous one, at least here in the United States, that I like to use has a total height of 93 meters. And I let you figure out which iconic American structure this is. There's another famous iconic structure that every engineer should know. This is in Europe, and that one has a height of 3 times 10 to the 2, or 300 in total, meters. And I let you also Google which one that is. You should be familiar with those two numbers. As an engineer, you want to know when it comes to structures which two structures I'm talking about here. So I wish you good luck finding that information. Now, if you deal with very specific sizes in certain branches of mechanics, or physics, I should say, then you deal with very specific subjects. And so, for example, if you deal with super tiny elements, so for example, on the atom level, then you talk about quantum mechanics, right? Then you would deal with quantum mechanics. If, on the other hand, you deal with super large elements, so for example, planets and so on, then you would use general relativity. And of course, those are topics we don't deal with here in this class. In fact, we deal with something that is called the macro scale, or the macroscopic scale. and therefore we deal with classical mechanics, is what it's called. And that is what we deal with here in this class. And I consider macroscopic scale anything that I can touch and still see like within close range, I want to say. So this is something that is our everyday scale. Any building that you are aware of, any structure, any car, those would fall into macroscopic scale. So we may want to remember that this includes things like cars, structures, projectiles, and so on. So this is what we deal with here in this class. And you could now take the classical mechanics and further subdivide it. There are things like Hamilton, Lagrangian mechanics, or continuum mechanics, fluid mechanics. We don't want to worry about this right now. If you really want to take a fun class that really breaks your brain, I would say start with something like continuum mechanics. And that is something that engineers deal with on a graduate level. And you then would need to be very familiar with that. And the only way you can understand things like, for example, let's say continuum mechanics. I'm going to make a side note here. Continuum mechanics. And the only way you understand continuum mechanics in your later career is if you have a solid understanding of classical mechanics. And that is true for other disciplines as well, Lagrangian, Hamilton mechanics, things that you don't even know yet will be ahead of you, but you will need classical mechanics to have access to that knowledge. So we are really starting from the ground up here, and kind of like the grandfather method of mechanics, which is the Newtonian mechanics. Newtonian mechanics. And that is the heart of this class, and everything we will deal with in this class is based on those principles laid out by Newton. And so we will talk about that. And to talk about that, we need to understand more about rigid bodies. And so let's now move into rigid bodies and what they are to us. And the reason we need to understand rigid bodies is because Newtonian mechanics deals exclusively with rigid bodies. And so I added these two pictures here to talk about rigid bodies. And I kind of put these pictures here to mislead you, because I think that most of us, when we start engineering careers or engineering education, have a misconception of this steel beam and then maybe even of the gummy bears in the context of engineering mechanics. Why am I saying this? So most of you probably at this stage in the education would believe that this is rigid. And that is true in engineering mechanics, but it's not true in the real world. In the real world, there's actually flexibility, elasticity to these types of beams, no matter from what material they are made. In this case here, steel, and we know steel is a very hard material, so steel we think is very rigid, and in a sense that is true, but there's still, again, elasticity to it. So you would expect elasticity from, let's say, for example, a gummy bear, because you can squeeze it and you can change its shape. And so in real life, this one here has really the tendency to make you feel like it's elastic and not rigid. But why did I put this here now is the question. Well, the reason is in engineering mechanics, rigid bodies are an idealization. So we idealize. So rigid bodies are an idealization. So what do I mean by that? We actually idealize both. This here, while you think it's rigid, it's really not. And this here, while you think it's elastic, if we use it in mechanics, we have to idealize it as well. We have to turn it into a rigid body. So now we're probably a little bit more confused, and we need to understand what is a rigid body. And a rigid body is something that does not change its shape. So no change in shape. So there's no shortening and no elongation, no matter how much force you put on it. So it doesn't matter if you put 20 tons or 100,000 tons on this beam here. If you consider it a rigid body, it will not deform. And by the way, the same is true for the gummy bear. So because we idealize it, it will be a rigid body that doesn't change its shape, no matter how much force you apply to it. So the way I do this in the classroom usually is I say, hey, there's one Raphael, right? And of course, everybody thinks of me as a rigid body, but it doesn't matter how much force you put on there. So we have the height of one Raphael, which by the way is a unit in this class, one Raphael. And it doesn't matter how much force you put on that one Raphael will remain one Raphael tall, no matter what. So that is signifying a rigid body. A rigid body means no change, no matter on the impact or no matter what physical action is acting on that body. No matter if you displace it, no matter if you put load on it, nothing will change its shape. And that is considered a rigid body. Now, there are two states that these rigid bodies can be in. So, for example, they can be at rest or they can be in motion. And we have to deal with them differently, and I'm sure you heard this before. If we deal with it at rest, then it is called a static analysis or static systems. Whereas if you deal with a system in motion, then you deal with dynamics. And dynamics is a very difficult beast in itself, and statics is already difficult to begin with. So in this class, we'll probably spend like 95% or 90 to 95% in this class is statics. And then later on, we move into dynamics if we have time at the end of the semester. So we really want to learn mostly about statics because it's the foundation for so many concepts. And of course, if you understand this really well, it will be easy for you to move into dynamics. But again, I want you to understand we have statics and dynamics. And the difference really is the acceleration. So this system is not under acceleration, whereas this system here would be under acceleration. So you can think of statics as a very special case actually. So this is special case of dynamics. Because it has zero acceleration, right? So acceleration is equal to zero. So I say it again, we have the state at rest and the state in motion, and if it's standing still we consider it static system, if it's in motion we consider it dynamic system, and the special case, the static system, comes from the fact that it's at acceleration zero, if you will. So therefore you can actually explain everything with dynamics if you set the acceleration to zero for static systems. But we have to start with the easier part, and so we devote most of our time to statics first before we move on to dynamics. But first, we are done now with the definition of the rigid bodies, and we can now move on to the definition of units and different measurement systems, and I will see you for that on the next page. All right, let's talk about a very basic concept that we all take for granted, but we need to understand where the units come from in our systems, or at least we need to have some appreciation for units of measurement. And why is that? That is because everything is relative, right? And because everything is relative, we need to have a universal agreement, right? In other words, the engineer in Europe needs to understand exactly what the engineer in Asia or in America has to say or wants to express. And so we need to agree on a unit and what that unit really means. So we cannot use the random unit of 1 Raphael. Of course, in this class we can, but in real life you need some universal agreement. And the things we need agreement on are actually threefold in engineering mechanics or in mechanics. And those are expressions for the length. We need something that defines the length. We need something that defines mass. And we need something that defines time. Because those 3 units are actually sufficient to describe everything else, believe it or not. We can derive all other units. And in the SI system, so in SI, we call this, as you know, of course, meter. Then the mass is actually the kilogram. And then we have seconds. So this is important to understand that here the mass is defined and the mass has actually a prefix in it. The kilo is actually a prefix. I will come back to that in a second. However, this system here is known to be the Mks system, right? So this is Mks system. And that is what engineering students often prefer. And they say, hey, I prefer the metric system, but you need to understand, we're not talking about the metric system, we're talking about the SI system. The SI system and the metric system, of course, go hand in hand with each other, but really the SI system is the system that defines the unit. And I will talk about each one of these in a second, just to give you something to talk about on your next engineering party. But you need to understand that this is not metric, right? The meter is not metric. The kilo is metric, actually, but the gram is not. The second is not metric either. So what I'm trying to express to you is that there's a difference between a unit and its prefix. And the definition of the units is what we really need to agree on. The prefix we can apply to everything. So for example, here you see an inch scale, and then here you see the centimeter scale. Of course, 1 centimeter is very different from 1 inch, but I could, of course, create a kilo inch or like a mega inch and so on, and that would be found in the metric system then. So you could have a metric inch if you want to. However, the system international, or the international system of units, as it's actually called, right? So let's write that down. So this here is called the international system of units. Actually defines these units in conjunction with the prefixes. So really, the international system of units is considered the modern form of the metric system. So let's write that down. And in that metric system, everything is designed around the number 10, right? So designed around 10. So that means you usually have 10 to the power of something. You already saw me using that before when I described the radius of the Earth or the radius of an atom. I used 10 to the power of something. And the reason the metric system is considered nice often is actually not because of the units, it's actually because of the prefixes. And that this is the kilogram stands for 10 to the power of 3. And the mega for 10 to the power of 6, and so on and so forth. But let's first dive in and talk real quick about each of these units, because it's so fun to think about that as an engineer. And I just want to give you some side notes here. So for example, the meter itself, right? The meter, I want you to think about how the meter is defined, or if you know this. And I really like how it was traditionally defined. Nowadays, of course, it's a different definition, but the very first definition of the meter was actually derived from a distance measurement on the Earth, so distance from the equator to the North Pole in a straight line through Paris. And then you take that distance and you would divide it by 10 million. So it's a 10 millionth part of that distance. And I think that's genius because everybody technically can recreate this, although it would be fairly difficult for some of us, but at least conceptually speaking, it's a genius idea at the time. This was derived in 1791, and at that time it was a way to standardize it such that everybody could validate it and it would be a defined measurement. Of course, this was then later changed and adjustments were made in 1927, and then later on we had much better technology. So for example, in 1960 we used the wavelengths of light, right? So wavelengths of light. And then some slight changes were made, but really we're still using the concept that was developed in 1960. And technology got a little bit better and we have higher precision, so that now we're looking at the light distance traveled in 1 divided by 3 times 10 to the 8 meters. So that's 300 millionths of a second. And we can measure that precisely now. But this is something which, of course, is not super relevant to mechanics. I just like this from an engineering standpoint because this is something that had to be invented out of nowhere. And this really shows ingenuity. And I think we as engineers can all appreciate that. So let's now talk about the kilogram and the mass. And the mass I'm talking about here is 1 kilogram. And the 1 kilogram was initially defined in 1800s, so in the 18th century, as the mass of 1 liter of water. And that is, of course, not ultimately true anymore nowadays because, as we know, water changes its density with temperature, and also we have other things to consider when it comes to water. So they adjusted this later on. I will talk about those adjustments in a second. But what's important is that this is almost still true. So 1 liter of water has the mass of 1 kilogram. And why do I like this as an engineer? Because we all are familiar with the mass of 1 kilogram because we all have seen 1 liter bottles or half a liter bottles in vending machines for like our soda drinks and so on. And so I intuitively know that I can lift 1 kilogram. Sometimes I meet students that say, hey, I didn't grow up in the metric system, so I have no feel for the kilogram. But here it is. Here's your kilogram feeling. You know that 1 liter of water is something you can lift, is something you have control over, and you have a feel for how that kilogram works. And again, we don't use this nowadays anymore. We actually now use a prototype, or even that got outdated now, but for the longest time in 1889, we developed a prototype. And pretty much that is just a specimen that was made from platinum iridium, and it was just declared as the reference mass. So think of this as a reference. And that thing sits in Paris, now in a museum. It's sometimes also called the Urmass, and that Urmass is really what we, for the longest time, balanced everything against. Nowadays, they made changes to that. but let's not worry about those. I just think this here, the 1 kilogram per 1 liter, is important. In fact, you will see in today's lecture why this is important for mechanics, because we can use this as a load on our structures and we can understand how our loads work. But more on that in just a second. Now we also have the seconds, talking about seconds, right? So we have the second, which was initially defined by the mean solar year. And that mean solar year was then divided into some fractions, in this case into 86,400 fractions, but we will not worry about those details here. And then there was adjustments made, and then we did it based on the tropical year. And nowadays we do it based on the cesium 133. So today it has something to do with cesium 133 atom, and really it has something to do with the radiation that is corresponding to the transition between some ground states, but that goes way beyond this class here, and I just wanted to add this here for completeness reason. These two things here I wanted to talk about because they make engineering sense to us and we can really visualize that, and we could even recreate it in one way or the other. And please note again, I said it before, that the kilogram actually has a kilo in it. So it's not just the entity that's described by the gram, it's also having a prefix. So let's now quickly talk about the prefix, because that is something we need in our work. So we have SI prefixes, and really they make our life easier. They reduce our workload or our writing effort. So they reduce writing effort. Why? Because they are a multiple of 3 usually. So like I said, 10 to the power of n, and then so we have 10 to the power of 3, 10 to the power of 9, or maybe even 10 to the power of -9, and so on and so forth. And you see some prefixes here in this table that I created for you. And of course, we need to complete this table. So for example, the mega here is 10 to the power of 6. And then we also have the centi, which is 10 to the power of -2. That's a very uncommon one here in America, but it's very common in Europe. We also need to understand that they all have certain names to them that you see here in the second column. So there's a prefix name. So a micro, for example, would be 10 to the -6. And then we have the nano here on the bottom. We know that. And all these symbols, or the 10 to the power or the prefix, replace a decimal. And I'll be very honest with you, when I did my undergraduate degree, I still refused to use these entities here on the left side, and I kept writing the decimals because I thought this is more precise for whatever reason. But that's complete bogus, because that everything after the 4th digit is irrelevant anyways. We talked about this in the 0 lecture when we talked about 4 significant figures. And so a lot of this is unnecessary writing effort, and that's why engineers technically prefer this. And the reason I told you about my undergraduate is because later on I actually made an effort to really study and learn these, and it really made my life easier, and I hated myself for not knowing that sooner. So I recommend that you forget about these, don't use these anymore, and move your effort to the prefixes or the symbols. And of course, we know that here now we need to add another 0.01, and then here the 0.1 is a 10th. And now we have that completed. And therefore, we now have a solid understanding of the units of measurements. Let me just tell you here on a side note that we also, of course, have the Imperial System, and my students in the classroom often dislike it, but we have to know how to deal with both. So for example, we have 1 foot, right, which is equal to 12 inch. And then we have 3 foot, which is equal to 1 yard. And then we have 1,760 yard, which is equal to 1 mile. I don't know who decided to keep this system because it is really tedious sometimes. As you can see here, they should have at least turned it into like a kilofoot instead of like a mile or something like that, or maybe a kilo yard. I don't know, something like that. It would have made our life easier, but this is what it is. And to be honest, if you know how to handle both of them, more power to you. It actually helps you to understand the world better, at least from an engineering standpoint. Now we also have the weight. And so I want you to understand that in the imperial system, we have weight and not mass, right? So the weight is actually defined in pounds. So the unit is pounds. And the corresponding mass would be a slug, right? So there's a slug that defines mass in the imperial system, but it's not a base unit. Please understand that. And of course, time is also in seconds, by the way. Time in seconds. So that's no different. But of course, you knew all that. So let's just go ahead and move on to our Newton's laws now. I will see you for that on the next page. All right, let's talk about one of the greatest minds in engineering and physics, and that is Sir Isaac Newton, who developed the Newton's laws. And I'm sure you heard about them before and you have dealt with them before. But let's find a common ground here. And let's talk a little bit about the idea of forces. So what does it take to describe a force? And then I want to talk a little bit about the history. When I talk about the individual Newton's laws, so I'm going to talk about Newton's first, Newton's second, and Newton's third law, and then also the law of gravitational attraction, which is very important. But first, let's think about forces. So we need, depending on who you ask, we need 2, or some people would say 3 quantities to fully describe a force. So you cannot just use a single number is the point here, right? A single number would be called a scalar, and you can use that to describe, for example, a temperature or a volume or something like that. But if you have a force in, let's say, a coordinate system, let's draw a coordinate system here. So I have like an XY coordinate system. And in that XY coordinate system, I want to have a force, and my force needs a length, right? So that would be one number that needs to describe that. And I need a direction, which is really defined by the arrowhead. And some people would argue, this is where the 2 or 3 comes from, that you also would need an angle, although you could argue that's by the direction defined. So it really depends on which philosophy you want to use, but you need to describe it with more than one number. And of course, you know this already. You know that you need to use vectors for that. But this wasn't always clear to every physicist out there. In fact, Sir Isaac Newton worked his way through that, and in the process, he actually developed the calculus for it. So we actually need vector calculus. Without that, we would be lost, and that's why we spend a lot of time in the early part of this lecture to talk about vector calculus. So we need more than scalars is the point here, and we need to understand how to deal with these vectors. And the first documented case that we know of nowadays that thought about forces and how they act are actually traced back to Aristotle, right? So you obviously heard that name before. And he really lived between 384 and 322 BC. And so it goes back a very long time. But the reason I'm mentioning him here is because he assumed that as soon as an object stops moving, there's no force acting on it. So he thought that no force, no movement. No force, no movement. And if you remember your physics class, then you already know that this is not considered true anymore, because we then had actually Galileo Galilei, and he lived between 1564 and 1642. And he actually was the first one to recognize that it requires a force to bring an object to halt. So force needed to stop an object. And honestly, I don't know why Newton gets away with his first law here, because he literally stand on the shoulder of giants here. He pretty much took the same idea that Galileo Galilei already used and turned it into his first law of motion. And so Isaac Newton really came along, and let's write that down as well, that Isaac Newton, who coincidentally actually lived between 1642, so right when Galileo Galilei died, to 1727. And in that time, he published a book called Philosophia Naturalis Principia Mathematica. And you can actually find a copy of that in the National Library online as well. And that is the book that claims to have invented calculus. Some people say that it was Leibniz who came up with calculus, but of course, as engineers, we believe that it was Newton. I don't know if that's true or not, but I choose to believe that. Anyways, in that book, he introduced some laws that we still use today. And what I find important to appreciate is that he came up with calculus. We sometimes complain about the things that we have to learn in school and that it's so difficult to solve these problems. This guy, Newton, actually wanted to solve a problem and didn't have the tools at the time, so he had to invent calculus. Can you imagine that? Inventing calculus to solve a problem, which he obviously successfully did at that time, but he had to invent the tools too. I think that's amazing. So more power to him. So let's talk about the laws, the first law first, and what it describes. And there are some definitions, you can look them up online. Galileo pretty much said that a body at rest remains at rest and the body in motion continues to move at a constant velocity unless acted upon by an internal force. And Newton pretty much stated the same. Let's maybe write that one down. He said that every body persists in a state of rest or uniform motion in a straight line unless it is compelled to change its state by a force impressed thereon. So that's how Newton reformulated Galileo Galilei's first assumption, and effectively they say the same thing. But what does that really mean? In consequence, that means to change a state is really dependent on how resistant a body is, right? So some bodies can be more resistant than others, and you know this is called inertia. So some bodies have high inertia and some bodies have small inertia. So in the classroom, usually I show a picture of a big boat, and I'm a great artist, as you will learn throughout the entire semester, but let's pretend this is a boat. And then I have a little fish here, and that fish has much less inertia, so this is small inertia, and this is large inertia. And the large inertia, as you know from everyday life, is very difficult to change in either motion or to bring it to rest. Whereas like if you have an object with like small inertia, then it is easy to change that state. And so the kilogram or the mass is really the measurement of inertia. And that is also something that we know from daily life, right? So large mass, large inertia. Large mass, large inertia. And that is because it's very difficult to change that state. However, we are now moving into Newton's second and third law, and before we do that, I want you to appreciate that like if these two swim into each other, and maybe my artist skills here should add some waterline here. So let's say there's some water there. And if they swim into each other and they touch each other, you may think that the fish actually pushes away from the boat, but in reality, the boat also pushes away from the fish. And that is something you should not underestimate, not because something is larger, it's kind of still relative to the small part. From an engineering standpoint, you always need to understand that both have an effect on each other if they hit each other, for example. But we will talk about that when we talk about Newton's third law. Let's first talk about Newton's second law. So for Newton's second law, that is something you obviously have used before, and that is force. It describes the force, and it says that force is equal to mass multiplied by its acceleration. And that is the reason why we need vectors. Because we know that the mass is really an integer, right? You can describe the mass by an integer. But the acceleration needs to be defined by a vector. Because acceleration is directed, it has a direction. And so what are the units here? The units are mass in kilogram. And then here we have meter per second square. And therefore we know that the force is really kilograms times meter per second square. And because that was defined by Isaac Newton, this unit actually became the Newton, right? So 1 Newton is equal to 1 kilogram multiplied by 1 meter divided by 1 second square. And I always invite my students in the classroom to explain to me what that unit really means and if they can have a feel for that. What is 1 Newton? It's kind of difficult to conceptualize initially what 1 Newton really is. And the story, of course, goes that Newton had this idea when an apple hit his head, and that is something that works. But in the classroom, and I wish I could do this right now, but sorry, we can't do this here. In the classroom, I hand out chocolate, and I like to hand out German chocolate. because German chocolate is usually delivered in 100-gram packages, right? 100 gram is one chocolate, one German chocolate, if you will. And so I encourage my student to really eat that chocolate, enjoy it, and never forget that it's 100 grams. And that is roughly speaking, actually in mechanics, it's exactly speaking 1 Newton. So please understand what 1 Newton is. And you may think, hey, I have heard about newtons before, I dealt with them before, but all the time in the classroom, I find that students have no concept of what 1 Newton is, or what is 10 Newton, or what is 50 Newton, or a kilonewton. But you can always relate it back to the 1 chocolate, and you know that you can lift a chocolate, you can eat a chocolate, but you may know that you cannot lift 10 million chocolates, for example, and so on. So you can always take that back to the basics. And in fact, I will in a second take this to the specific weight of water, something we can also trace back to this concept. But before I do that, I just want to emphasize one more time on this force is equal to mass times acceleration. And that is because it's intuitively pleasing to think of this, right? So the stronger the force on an object, so the higher the force, the more it accelerates. Let's write that down. So more force leads to more acceleration. And you know that, right? You can try this. Take, I don't know, your house keys and throw them with a little force or throw them with high force, and you will see that they obviously accelerate differently. Likewise, you know that if you have something with more mass, then it is more difficult to change the acceleration. So more resistance to acceleration. And you can try this too. Try throwing your key or try throwing your desk, right? Both of them have different mass, and the one with the lower mass probably accelerates easier. And this is all found in this equation. And again, the unit is kilograms times meter per second square, but really we call that 1 Newton. Now, we already talked about the fact that 1 liter of water, 1 liter of water is equal to 1 kilogram. And so we know now that 1 kilogram is equal to 1,000 grams. And therefore, we know that 1 liter of water really is 10 Newton, right? Because it's 1 kilogram. So 10 Newton per 1 liter of water. And why am I telling you this? Because in this class, take this as a word of advice. In this class and later on in engineering, you will see many problems where you have to fill a volume with water. And we will not tell you what the force is on the system. We will just tell you, hey, there is 1 cubic meter of water, or there is 500 liters of water in the system. So how many newtons do you have? And the best thing that you should find out, take this as a homework, is how many kilonewton per cubic meter of water do you have? So I want to know from you what that is. If you have 1 cubic meter of water, so 1 cubic meter of water produces how many kilonewtons? Because this is the unit that you will see over and over again later on. So you will see problems where you have to deal with forces that have a kilonewton acting on them, and then you will be given a volume in most likely cubic meters, and you can then use the specific weight of water, right? So specific weight means a weight per volume, and keep in mind that this is a weight, kilonewton, right? And in the Imperial System, this would be pounds per cubic foot, for example. But here we're dealing with the metric system or the SI system, and so we're looking at kilonewton per cubic meter. And I want to know from you, I could write it here, but I'm not going to do that, but you will see it over and over again. You need to know this, so find this somewhere on the internet or work out your own way here. Find out how many kilonewtons you have in 1 cubic meter of water, right? And that, of course, we do with G being equal to 10 meter per second square, right? So meter per second square. We talked about this in one of the 0 lectures. So please understand that G, the gravitational constant here now, is 10 meter per second square. But this is important. Find out what kilonewton per cubic meter is produced if you have a volume filled with water. All right. I think with that said, we are now ready to move on to Newton's third law, which of course you have used before as well. And you know that every action on a system is equal to an opposite reaction, right? So and that is something which you may think is super easy, but when we come to part 2 is the thing we always violate. Or in other words, every time we lose points on an exam or on a quiz, we will find that we violated this rule. And this happened to me all the time when I was a student. Although we think that this is so easy, it's the easiest thing to overlook, right? So it's kind of stating that the sum of the forces is equal to 0, right? And that is also intuitively pleasing because you experience this in day-to-day life. For example, the chair you're currently most likely sitting on, you push down on it with your weight, but the chair is also pushing back on you. So examples here would be you're sitting or you're standing on the floor. Let's say you stand on the floor, right? You push down on the floor, but the floor is really pushing back in the opposite direction with the same force. Likewise, if you ride your bicycle, you apply force to the pedals and the pedals push back on you. And then also you turn the wheel into motion and the wheel then pushes on the asphalt and the asphalt pushes back, and that's why you move forward. Or like ice skating, right? So if you have ice skating, this is why you need sharp blades, right? Because only those can create the resistance between the ice and the ice skates that you wear so that you can actually push yourself forward. Otherwise, you would not be able to move on the ice. Or the same is true for walking, by the way. Like the only reason you can walk forward is because you push yourself forward and the resistance or the friction between your shoes or your feet and the ground allows you to move forward. And that is Newton's third law, and we will have a lot of fun with that. So that completes our Newton's laws, and we now have a solid understanding and a base ground for what's coming up. You may think, hey, why did he bore me with this? I learned all about this in physics. And again, if something goes wrong in this class later on, it can mostly be traced back to this equation here or to this concept. And to understand this concept, we also need to understand these. And I want to point out one more time the importance of the density, or in this case, the specific weight of water. So please have that accurately available when it becomes necessary. But now let's move on to Newton's gravitational law. All right, let's now take a look at my favorite Newton's law, the law of gravitational attraction. And for that law, we probably heard this before, that everything attracts everything. That, of course, is not very scientific, but we're trying to say that if you have two objects, for example, here we have M1 and we also have M2, and both of them have a distance to each other. Let's call that distance R. So there's a distance R between the two, and it has been shown actually experimentally that the gravitational attraction between M1 and M2 is really proportional to the product of the two masses and inversely proportional to the square distance r. And we will write this down as a formula in a second. I don't expect you to memorize this just because I say it, but please understand that the attraction between the two masses are really dependent on the amount of the mass, and the more massive they are, the more attracted they are to each other, and they are also inversely proportional to something with the radius here, or the distance, I should say. And that is, the further away they are from each other, the less attracted they are. So that's why in the classroom we always come to the realization that, you know, we should go to the bar next time and find the person that we like and tell them, hey, do you know that you are attracted to me? Because everything is attracted to everything, right? And if you don't believe me, just come closer, you will be more attracted to me. And this can be expressed in a formula. You can say that there's a gravitational force between the two masses, and you know that you found the right person when you can talk about formulas, right? So maybe you can even extend that conversation there. But the formula that you want to talk about is M1 is multiplied by M2, and that then is divided by the squared distance, and we need to add one more thing, which is the gravitational constant. So what we have is the two masses and divide them by the distance. And this is very important for structural applications, because that is how forces are created really here on Earth and actually everywhere, but we have a specific value to them when we deal with them here on Earth. In fact, so understand that M1 is the mass of the first object, mass of the second object, distance between them, and the gravitational constant. And I will not ask you to remember this, but we will use this number in a second. So I will just tell you that this here is 6.673 times 10 to the minus 3. And the unit for that is meter cubed divided by kilogram times second square. Again, you do not need to remember this. Maybe you remember this from your physics class, but it's just a number we need to make this all work here. In fact, I want to talk about how to make this work for the gravitational pull here on Earth, right? So if you, for example, bring the two objects so close together, so consider this being Raphael and this being Earth, then you have a radius here, right, of the Earth, and that radius then would be, let's say, equal to 6.37 times 10 to the power of 6 meters, that is. And so the mass here, m Earth, would be equal to 6 times 10 to the 24, and this is in kilograms. And so then you can actually replace some of the parts if you now consider this piece a structure and you put it actually directly on the surface of the Earth, because then your formula effectively turns into F is equal to M1, which is the Earth in that case, times uppercase G, and then you divide that by R squared. And of course, these are the values for Earth. So this is everything that happens on the planet here, but you still would have to multiply it later on by M2. But think about the values that you're using here, right? So here you would use the 6.673. For R, you would use 6.37 times 10 to the power of 6 meters. And then for M, you would use 6 times 10 to the 24. And that is in kilograms. And I invite you to calculate that, and hopefully you find the number that already pops to your mind, but you should calculate this value. I'm not going to do that for you here right now, but I expect you that you know that. What is this value? I want to know that from you if you use all these constants that I already provided for you here. And then once you found that value, you understand how we calculate forces that really act on structures. And if you really understand the concept of this attraction, then we can actually enlighten you on one more concept that you probably heard before, but my experience in the classroom is that everybody knows that we say, hey, if you have Earth here, right? And we have the moon here, we know that the moon affects the tide on Earth, right? Like how our water behaves in our oceans. The question is why, and the answer is Newton's gravitational attraction. So how does that work? Well, we have water on one side of the Earth, if you will, and we also have water on the other side of the Earth, right? And there's obviously mass to this water, and there's mass to this water. Then we also have mass to the moon. So we have mass here. But what's more important to understand is that we have different distances between the individual water bodies, if you will. So we have this distance here. So let's call that R1. And then we have here R2. And of course, this radius, I say radius because of the R here, but really the distance here is much shorter than the distance to this water, and therefore this water has much higher attraction to the moon than the water on this side. In reality, of course, there's more complex systems at play, but this really explains what happens and why our tides are affected by that. And I think in your homework you have a fun exercise to think about what happens at new moon and what happens and other times of solar constellation. But I let you work that out. Last but not least, I want to leave you with these images here, and I want you to think deeply about the difference between this scale and this scale. They're both called scales. This is actually more precisely called a balance, and this is a scale here. But there are differences to these, and I want you to think about, so think about the differences of these two scales or balances, or however you want to call them. Again, this is a balance or like a beam balance, and this is a scale here. But they have different mechanisms that make them work. So they have working principles. And I want you to really understand why they work differently and when would they actually give you the same results and when would they give you different results. So when would the measurement be equal and when would they differ? So what I'm really asking you here is, hey, where would you have to place these to read the same measurement, or where would you place them to read a different measurement? And I wish you good luck with that, but I think you can answer this based on everything we have talked about on this page and the previous pages. So that concludes our lecture for today, and we can now move on to the concluding page and our checkpoints. All right, time to complete our final takeaways and our questions for the lecture. So please go ahead and ask yourself, what have you learned and what is the things that you can take away from this lecture? And then more importantly, ask yourself what is still a little bit foggy in your mind and try to find ways to get clarification on that. But once that's the case, we can move on to our final checkpoints and the few takeaways from this lecture. So I hope you can agree that you now understand the significance and the meaning of each Newton's law. And if you do, then please check this box off with me. You also will not forget what the meaning of 1 Newton is, and you can hopefully relate that to the real world. That's really important here because you will be asked to do that over and over again in the future. Then we will never forget the density or the specific weight of water. And we talked about that, and you have to, of course, calculate that yourself, but make sure that you really get the correct number there. And last but not least, we understand that Newton's law of gravitational attraction is really used to derive some of the basic principles here for forces on the planet Earth and actually forces everywhere. But you have now full mastery of that law of gravitational attraction. And with that said, I believe we are now ready to tackle our very first homework. Let's move on to the homework page. All right, everybody's favorite is the homework, of course. And before we talk about the individual problems here, let me first tell you the very important thing that is marked in red here, that this is a homework that's very different from the other ones that you see. This is considered a training homework. And so the problems are actually very short. This will not be the case in the future. And we have some rules about the homework in this class. And one of them is to have 1 problem per half page. That would be a waste of paper in this case. And so in this exceptional case here on homework number 1, you can add more than 1 problem per half page as long as your work remains legible. But legible also means that you have distances between where a problem ends and the next one begins. So do not cramp them close to each other. Make it easy on yourself and your TAs to actually be able to see where your work begins and where it ends. And then the first thing you have to do is agree that you understand all the rules in this class and the homework format, just so that we are on the same page about that. Then we have some Newton law problems for you here. I don't think I have to say much, except please print these pictures. So for example, here you have to find an object of a body that has a weight of 2 Newton and another one that has a weight of 10 Newtons. Often the students are confused what they should do with that. So just take a picture of the object with your cell phone, and then usually you print it if we meet in class, but you just attach it to your PDF file if you submit it electronically. And the same is true here for the Heroes engine. So build a Heroes engine, take a picture of it, and then add it to your submission in your file. And I think those are the most common questions that I usually receive about that. And hopefully I was able to answer that. Now, this part here, unit conversion, relies on the concept of the variables. And I call this the homework variables. You know this, you calculated that through your 4-digit ID. And you can calculate your individual numerical values at this website. You probably did that already. But then the idea here is that you get used to them. And please understand that for the purpose of this homework, do not include any units. In fact, units do not come from the sheet that you get here. Units are always included here. So F1 is unitless on your piece of paper. It just happens to be a force. W1 is unitless. It just happens to be a distributed force. A is unitless. It just happens to be used for distances in this class, and so on. And so in these problems here, what you see in bold print is really the variable that comes from your homework sheet. And then here are the units that you have to play with, and you have to rearrange them. And you can either use prefixes or the short symbol, but I guess here it asks you to use prefix. So you need to take the symbol and turn it into a prefix. So the prefix 10 to the power of something. And I think that completes that problem. Then you have to work with other units here as well, but I think that's all the same. I don't need to explain much here. You can really read your way through that. Please make sure that here for number 3 you use 4 significant figures. This again is a training exercise. In the future you will always use 4 significant figures and you will always lose points if you don't. So this is the first time where you do it, and we can explain to you why that is. And so here you can still make mistakes, but later on that will cause point deduction. And so we want you to practice it here. And conceptually speaking, this homework is not very difficult. It's not very engineering mechanics-like, but it gets you in touch with your variables and it gets you used to the format of the homework. We have another page to the homework. In this case, usually it's only on one page, but let's take a look at the next page. So last but not least, for this homework, you have to express the surface area of the Earth with 4 significant figures using proper prefixes, using these units. So it's effectively also unit conversion, and I'm pretty sure you can Google this part, right? And then here we ask you about the Statue of Liberty and the Eiffel Tower, and if you can express that in specific units. So this is all getting used to units and so on. And I don't think there's much I have to say here. I think it's all self-explanatory. But if you have questions, you know how to reach me, and we will have other opportunities to interact with each other before you submit this homework. So I wish you good luck studying with this, and I hope you have fun with your first engineering mechanics homework. Enjoy it as much as you can. I promise you, in this class, every homework is targeted towards a specific learning goal. And so don't skimp on it. Do not take any shortcuts, because shortcuts always hurt the student in the end. I know you hear this from every teacher, but I really mean it. I put a lot of effort into this class to help you, to help yourself. And if you try to trick yourself, then this all falls apart. So please be smart about it and work harder and smarter. So again, I wish you good luck with the homework. I'm looking forward to a fun semester, and I will see you in the next lecture. Until then, stay safe.